This subject, I would say that power lines are like this flexible plastic tubing, and the electrons inside are like this chain. So what a power station does is it pushes and pulls the electrons back and forth 60 times a second. Now at your house, you can plug in a device like a toaster, which essentially means allowing the electrons to run through it. So when the power station pushes and pulls the electrons, well, they encounter resistance in the toaster element, and they dissipate their energy as heat, and so you can toast your bread. Now this is a great story. I think it's easy to visualize, and I think my students understood it. The only problem is, it's wrong. For one thing, there is no continuous conducting wire that runs all the way from a power station to your house. No, there are physical gaps, there are breaks in the line, like in transformers, where one coil of wire is wrapped on one side, a different coil of wire is wrapped on the other side, so electrons cannot possibly flow from one to the other. Plus, if it's the electrons that are carrying the energy from the power station to your device, then when those same electrons flow back to the power station, why are they not also carrying energy back from your house to the power station? If the flow of current is two ways, then why does energy only flow in one direction? These are the lies you were taught about electricity. That electrons themselves have potential energy, that they are pushed or pulled through a continuous conducting loop, and that they dissipate their energy in the device. My claim in this video is that all of that is false. So how does it actually work? In the 1860s and 70s, there was a huge breakthrough in our understanding of the universe when Scottish physicist James Clerk Maxwell realized that light is made up of oscillating electric and magnetic fields. The fields are oscillating perpendicular to each other, and they are in phase, meaning when one is at its maximum, so is the other wave. Now he works out the equations that govern the behavior of electric and magnetic fields, and hence these waves. Those are now called Maxwell's equations. But in 1883, one of Maxwell's former students, John Henry Poynting, is thinking about conservation of energy. Now, if energy is conserved locally in every tiny bit of space, well, then you should be able to trace the path that energy flows from one place to another. So think about the energy that comes to us from the sun. During those 8 minutes when the light is traveling, the energy is stored and being transmitted in the electric and magnetic fields of the light. Now, Poynting works out an equation to describe energy flux. That is, how much electromagnetic energy is passing through an area per second. This is known as the Poynting vector, and it's given the symbol S. And the formula is really pretty simple. It's just a constant, 1 over mu naught, which is the permeability of free space, times E cross B. Now, E cross B is the cross product of the electric and magnetic fields. Now, the cross product is just a particular way of multiplying two vectors together, where you multiply their perpendicular magnitudes, and to find the direction, you put your fingers in the direction of the first vector, which in this case is the electric field, and curl them in the direction of the second vector, the magnetic field. Then your thumb points in the direction of the resulting vector, the energy flux. So what this shows us about light is that the energy is flowing perpendicular to both the electric and the magnetic fields. And it's in the same direction as the light is traveling. So this makes a lot of sense. Light carries energy from its source out to its destination. But the kicker is this. Poynting's equation doesn't just work for light. It works anytime there are electric and magnetic fields coinciding. Anytime you have electric and magnetic fields together, there is a flow of energy, and you can calculate it using Poynting's vector. To illustrate this, let's consider a simple circuit with a battery and a light bulb.